Hi, my name is Nick Schrock, and I'm the CTO and founder of Dagster Labs. And welcome to the last day of launch week. It's been an awesome week, and we've launched a ton of new features and exciting new capabilities. And as you'll hear me, if you'll hear me say a few times, the focus of the week has been empowering the developer, the engineer, with composable, embeddable tools in a data platform while still having it feel cohesive. And today, we're going to be talking about taking this philosophy of flexibility, composability, and embedding, and applying it to Dagster itself. And that's why we call this talk Deconstructing Dagster. And we're going to do that by launching two super exciting new features. One is called external assets, and the other one is called pipes. So just a reminder of what we were covering during launch week. Again, everything fits into this theme of composable, embeddable tools for data engineers. One is building data quality directly into the orchestrator. We think this is an exciting development, and we think once you have data quality in the orchestrator, you never want to go back. Data quality should be part of the day-to-day work of data engineers. And so the orchestrator is data quality aware, but you can bring your own tool, whether it be dbt tests, Great Expectations, or your own Python libraries. Next, we launched Embedded Insights, which is effectively analytics on the data platform directly built into the orchestrator. And the primary use case, or the showcase use case that we launched with, was using this to control costs and to control resource consumption of your data pipelines, and do that all within the orchestrator and empower the engineer to understand and fix those problems. On Wednesday, we talked about education. And this took the form of two launches that day. One was Dagster University, which is a learning resource for getting up to speed on Dagster, both for data practitioners, who kind of have to learn the entire system, and also stakeholder education, meaning, as a data engineer, you are interfacing with other stakeholders in the data platform very frequently, and it's important to get the right information to the right people. The other thing we launched as part of kind of the third day, education day, is that we open sourced our own data platform, which I'm really excited about. One, it's a showcase of how to use Dagster. And second of all, it's like a really interesting reference implementation for anyone who's building a complex modern business, especially a SaaS tool. We do our own billing, metrics tracking, we track our open source community usage, all through that tool. Last, on day 4, well, it's not last, today's last. On day 4, we covered embedded ELT, which is a new style of integration for doing data movement, the act of moving data from, say, an operational store to the data warehouse. And it provides an alternative path where you can bring in a library that does data movement directly into the orchestrator, as opposed to having to bring in a parallel heavyweight stack that is only purpose-built for that solution. And today we're going to be talking about deconstructing Dagster. So what do I mean by deconstructing Dagster? Well, let me give you some context. We talk to our customers and users all the time, and we get a lot of feedback. We get positive feedback that it feels really powerful, feels really elegant, the tools are great, and we love hearing about that. But we also get critical feedback. A tool like Dagster is central to data engineers' day-to-day life once they adopt it, so they rightfully have strong opinions on it. And critical feedback it ends up being flavors of the same thing. So sometimes what we hear is like, oh, it feels like too much at once. You kind of have to adopt Dagster for everything. Therefore, it doesn't feel as approachable because I feel like too many concepts are front-loaded. It's not incremental enough, especially to bring my peer teams in the data platform on board. It feels like it's all or nothing. And then similarly, we also hear it's kind of this inflexible vertical integration. Like it feels like Dagster is trying to do a bunch of stuff. What if I only want to use one component of it? How do I do that? And we think that this feedback, it is all symptoms of the same underlying cause, which is Dagster itself was not composable enough or flexible enough. And this release, the explicit goal is to change that. And by changing that, we think we're not just going to address that feedback, but we also think it kind of opens up the world to us to really expand the orchestrator to more use cases, to make it dramatically easier to deploy across the organization, and really credibly be a truly universal control plane across your entire data platform. It's no longer a pipe dream. This makes that possibility a reality. So we talk about the discussion, I mentioned vertical integration. What are we vertically integrating? And what we came to realize is that Dagster is really a layered system. And I'm going to talk about 3 layers of it right now. Kind of the natural question is like, you say you're decomposing, but like, what are you decomposing to? Well, we're really conceptualizing Dagster right now as 3 layers. So 1, it's a metadata platform. It is a place to track the metadata about the data platform and all its constituent data assets. We have this really powerful data structure we call the event log. It's this immutable log of events. You can think of it like a ledger that keeps track of everything that happens in your data platform. When assets are materialized, if they're observed, metadata about them, their data quality checks. All of this is driven by this event stream, this event log. Our kind of reactive, beautiful tooling is all driven from listening to that event log, and we overlay analytics, scheduling, alerting, and other capabilities on top of it, and our entire cataloging tool, right? So it's this metadata platform, really important. Second of all, of course, there's orchestration, right? Dagster is traditionally categorized as an orchestrator. We view it as more than that, but that's kind of the box that we're put in. So we're compared against tools like Airflow, and the orchestrator, yes, we do that. It's a place where you can schedule and run the computations that drive your data pipeline. Very important capability. And third, we're this sort of opinionated Python framework for structuring the business logic of your data pipelines in Python. I just said Python twice, but it's okay. It's a framework in Python. And really the goal of that is to structure your code so developers fall in that pit of success where they can automatically end up with more modular, more testable code. And we are big believers in testability. We think it's the foundation of high quality software as well as the ability to productively build software. So 3 layers here. And what we're effectively doing here today is launching 2 technologies that cleanly separate different layers of the stack. So the first one is external assets. And what external assets allows you to do is to use Dagster as a metadata platform while still using an external scheduler. So you can use our asset graph, you can track data assets in the catalog, but from the external scheduler, you can in a very lightweight way instrument that with API calls. It can be a REST call, it can be just a Python API, and call back into Dagster and let us know what happened. And this allows you to use Dagster as a really powerful observability platform without having to do a heavyweight migration of your orchestrator. Next, we have pipes. And just like how external assets separated metadata from orchestration, what pipes does is provide a clean separation between orchestration and business logic. And critically what this means is that it allows you to launch compute into an external environment like a Spark cluster or a hosted ML runtime or a Kubernetes pod that has a completely different environment, but do so in a way where the computation on the other side feels like a first-class citizen in the Dagster ecosystem. You can pass parameters to this thing seamlessly. You can get streaming logs and metadata back to the orchestrator, and it really feels like a first-class experience, but you also get that separation of orchestration and business logic, which is often highly desirable and sometimes completely necessary. So we're going to be exploring this through a very concrete use case. And the use case is the following. So you're at a company, there's a multi-team data platform. There's a new ML team that has gotten spun up, and they've gotten a little momentum going, but it's clear they need an orchestrator. They interface with a data engineering team. And that data engineering team has been around for a long time. They have a data lake on S3. They're using Airflow, and that's the way it is. And they have what they really want, and they believe, is that they want a unified layer of software to track lineage, quality, alerting across both of those teams, right? That is their stated goal. But the ML team does not want to use Airflow because Airflow is really not suitable for ML use cases. And there's particular issues about it they don't like. And so they, the platform engineer and the ML team is like, okay, we got to figure this out. So they go talk to the data engineering team and they say, hey, we want to get everyone on the same scheduler. We want to use Dagster, right? How about you guys migrate to Dagster too? And the data engineering team is like, hey, instead of doing that, how about we don't do that? How's that for an idea, right? Frequently migrations are risky, heavyweight things. People don't want to do them. Incentives are not aligned. Scheduling is not aligned. And what that can lead to is that, you have this organizational impasse that leads to technical fragmentation. So what's the solution? And the solution is to deploy a system that the ML team can use for scheduling and metadata and all that stuff, get all those features they want, but allow the data engineering team to opt into the system for the additive capabilities that Dagster provides, lineage, data quality, observability, and so on, and do so without migrating their orchestration infrastructure. And they can do that with external assets. So this is the existing situation on the data engineering team. They have a YAML file which defines their kind of DAG of assets. They already have like this own internal DSL. If you're an Airflow user, this is what it looks like on the right. They actually have some code which programmatically creates an Airflow DAG. We see this in a super common situation. So the first step that you need to do in order to onboard this team onto Dagster is you need to ingest that YAML file, write some code, and produce some asset specs, we call them. They're descriptions or specifications for an asset. And right away, the moment you do that, now, boom, it appears right in the UI. Now you want to be able to make that asset graph come alive, right? You want to be able to track metadata. You want to know when it was updated last. Critically, you want to be able to schedule downstream computations by the ML team based on when things kick off in the data engineering team. So this is where the magic of external assets really comes into play. We hook into S3, in this example, we're gonna hook into S3 event notifications and set it up so that every time there's a write into the S3 data lake, it calls back within a Lambda to this function. And this function says like, hey, this S3 path was written. We're gonna post that to request, call to our Dagster installation, and then all of a sudden, boom, one line of code, you have a single pane of glass for your entire platform. Let's see what this looks like for real. Okay, so let's do a quick live demo here. What we're looking at is more live code that I showed you on the slide. Again, as a reminder, we have this pre-existing data lake format used by the team by the data engineering team that they use to programmatically generate their Airflow DAGs. We write a little parser, it's not too bad to write, which parses that YAML and then produces what we call asset specs, which is a pure metadata specification of an asset. And then we call this function external assets from specs and pass it into our definitions object. And the moment we do that, we have this loaded up into Dagster UI. And it's the same Dagster UI that you know and use. It's nothing's different about it, except these are assets which cannot be materialized within Dagster. But we're modeling them and they're actually being scheduled somewhere else. So let's kick off that other scheduler. So I just did that off screen. And now what we're gonna see is kind of these events coming in, right? So we have that same live updating asset graph with all that meta information in it. So if I click on here, we see that, in the materialization in the last run, it came in and landed this URI, it is of this size. I can go in, look at it in the asset catalog, get its information. As more data lands, and I think it's going to be kicking off, it runs about every 30 seconds. As, more stuff comes in, it's updating right now. So actually this upstream data indicated there's new upstream data. Now it's updated again. We can go in here. Now we have a second, we have a second event reported, and this time it actually was at a different partition. So that's how this works and how, we're now tracking assets that are materialized elsewhere right within Dagster. So we just finished our demo of external assets, and now we're going to move on to the next part of our data platform journey. And we're going to talk about this ML team again. Now, the ML team is the reason why Dagster is being brought in the organization in the first place. They're just getting their team spun up. They've been using Kubernetes almost primarily. They upload Kubernetes containers, they run them, they schedule them with Kubernetes cron jobs, but they know they're going to need an orchestrator to manage Dagster compute. So they prototyped scheduling on Airflow because they knew that their team upstream used it, but they hated it. And we'll get into those reasons why. And they like Dagster a lot, in particular, the one engineer is kind of the champion. But they've already invested in a bunch of code, and they actually want to run each of their jobs, each of their tasks, I should say, in bespoke Kubernetes containers. Like each data scientist kind of has their own dependencies, and they don't, want to like really have purpose-built containers for every computation. And so this leads to a problem. The one engineer who is really jazzed up about Dagster and all its features, like, hey, we can use this great tool. All you have to do is migrate your code and restructure it in this way. And also you have to bring in Dagster, and it has a bunch of dependencies, add that to your container, but it's not a big deal. Why don't we do that? And then the other data scientists and ML engineers in the team reply, how about we don't do that? I don't want to restructure my code. I don't want to add more weight to my containers, right? Your stuff might conflict with my stuff. So let's not do that. So we have another alignment problem. And what the solution that we can provide is, and that's what we're launching today, is what we call pipes. And I'll get into what it is in a second, but what it allows, for this ML team, what it enables is that they can set it up so they can launch compute in the remote Kubernetes pods. They can pass parameters, pass context. They can do so reliably and seamlessly. And then they can get metadata and logs back from those computations back into Dagster. And again, do so in a seamless fashion. And still, it feels like the code in that remote container feels like a first-class participant in Dagster. Let's dig into what that really looks like. So what is pipes? Here's kind of a high-level view of it, right? You have code executing in the orchestrator. You have the full access to all of Dagster. And what allows you to do is launch code into that external process. In this case, it's the case container. You can pass along context information like partition key. If you're coming from Airflow, that's kind of our equivalent to execution date. It's just more flexible than that. In the external process, the dependencies are very lightweight. You have to bring in one library, which is just actually about 1,000 lines of Python with no dependencies, and you don't have to change that much code. And then that can stream logs and metadata back to Dagster so you can use it as that control plane. I think interestingly, we really think about this as a composable RPC protocol, meaning that you're invoking remote computations. But what pipes does is it actually is agnostic to how the compute is launched. That means you can kind of have a standardized way of shipping around context information and metadata in a way that's pluggable. So you can use the same data structures and a bunch of the same code if you're launching, say, a job in a Databricks cluster versus a ad hoc Kubernetes pod. So it's really powerful. It solves a very thorny problem in data engineering, which is invoking remote computations and like shuffling around parameters to it and doing so seamlessly. Let's talk about what was the problem with Airflow, right? I kind of just claimed that the ML team didn't like Airflow. There's a few reasons for it. Like Airflow is kind of clunky to parameterize. And in general, kind of it's well known for not being great for ML use cases for that reason. But they also didn't like the way that they had to wire everything up to get remote Kubernetes pods executing. Really, this is a very encouraged pattern in modern Airflow programming, where instead of using their built-in operators that execute with all sorts of different types of technologies, you instead just use a single operator. And that's the Kate's pod operator here. But it's still very clunky to use. In effect, it is up to the user to hand roll a pretty complex interaction. In fact, you can think of it as like an ad hoc protocol. Typically users have to write a bespoke CLI application for every task, right? You'll see here it's shuffling along execution date as a command line argument. On the other side, you have to know how to do it. This is an extremely simplified version of this. This can get awfully complicated, or engineers have to build an entire framework around this. Similarly, if you want to get information back out of the remote computation back into the orchestrator, Airflow provides this like very awkward mechanism where you have to plop a JSON file at an exact hard-coded file path in the remote container, and then Airflow knows how to grab that and it jams it into a system called XCOM, which a lot of Airflow people don't even recommend using. So this ends up being a very awkward interaction that you generally have to re-engineer kind of an ad hoc lightweight protocol over and over to get it to work, and even then it's still clunky. So contrast that in a world with pipes. So in this case, we have standardized clients. In this case, it's a pipes K8s client, but it implements the same interface if you're doing Databricks or just invoking an arbitrary subprocess, or I should say a very similar interface. It kind of, it's very easy to move compute or to use these clients in a uniform way. And then in the remote process, right, you have to bring in this library, right? This library called Dagster Pipes. It's very lightweight. You make a call in the bottom here to open Dagster Pipes, and you call your main program as before. You use the existing business logic that you had, but you'll see here, instead of having to manually move around CLI parameters, passing the partition key is directly built in. You just grab it off the context. And then you're able to call things like report asset materialization and report asset check directly as first-class API methods, and that gets transmitted back to Dagster. And you'll note here, and I want to continue to emphasize how lightweight this is, right? Dagster Pipes is a lightweight dependency with no additional Python dependencies, and really you have to minimally change your code in order to plug into Dagster Pipes in a first-class way. Let's switch to a demo here. So let's look at some real code here to show how pipes work. So we have the assets, the external assets that we had loaded before. But what we're doing here is we want to add a downstream asset that uses pipes to invoke a computation in a Kubernetes container. We're actually hooking it up by adding the sensor. And what this does is this sensor listens for materializations that happen upstream and will kick off this whenever that happens. Okay, so we have a pipes K8s client and we have a Kubernetes container that's loaded up in here. And according to the comment here in the description, this Kubernetes container contains join IoT. So we kick off this run here. And let's go to join IoT. And what's going on here? Well, imagine this is kind of a placeholder, but imagine we had some business logic here that loaded data and transformed it. And in order to kind of invoke that, what we do is we just do this very lightweight call. We open up Dagster Pipes, we log something, we do the existing data transformation, and then we can report the asset materialization. We really haven't had to add much code to have this participate in a first-class way. Okay, now let's view that in the UI. So we'll see here, let's go to global asset lineage. And you'll see here, we're starting off with a clean, let me move this over a little bit. We're starting out with a clean lake here, so nothing's been materialized. And now this new asset, right, this is one that's pipes, is downstream from this data lake. So you can already see we have our so-called single pane of glass here. I'm gonna go over here, check this sensor over here is running, and this is listening for this asset to get updated. So I'm going to kick off the assets materializing in the lake, and now we can see these come in. If we go back to the sensor, in a second it's going to kick off because it will have registered that there's a run happening. Okay, so now it kicks off. And you can see here, I'm showing you the value of how all this fits together to make it so that you can really compose a platform. So we had the external assets that was being scheduled. We had a sensor in Dagster listening to whenever it was updated. And now Dagster is kicking off a job, kicking off a Kubernetes container. And then it's actually getting reported back right here, this finely structured metadata. And it had also passed in a partition key into it. And so this is all super, super powerful. So you see here, this is the partition that was passed in. right? And the events, it showed that I did 1,000 rows. And so this is all this integrated system, and it's super, super powerful. So we just showed you how pipes can invoke an external script, pre-existing script with just a couple lines of code. You can annotate it effectively and stream back metadata and also pass parameters to it. And we actually showed you how this worked in concert with external assets. So in one demo, you saw a external scheduler streaming events back to Dagster, then a sensor listening for that and then kicking off a run, which in turn via pipes kicked off compute in a Kubernetes cluster. And all looked this seamless experience in this beautiful UI. But we're not done yet. And there's an interesting fact about the world, and that there are more programming languages than Python. The world is not Python. And this is an issue that pipes can actually help a bunch with. And the reason why is that pipes is a language-independent protocol. So what I mean by that is that if we go back to this picture, again, we were decomposing Dagster into metadata, orchestration, and then business logic with this little bit of a library on top that kind of facilitates the protocol. But with pipes, that business logic can, as we go forward and mature the system, be in any programming language. And this opens up the world for data platforms to additional tools and to bring additional personas into the data platform. So here's our scenario that we're going to demo. The scenario is the following, which is that the data engineers on the ML engineers, pardon me, on the ML team were actually very passionate about data quality tests, but they felt that it was too expensive to do them. Like they're computationally expensive. They were checking if there's no nulls in tons of different columns and having to walk these extremely large data frames of memory. And one very intrepid engineer on the team had the idea, well, they were saying, listen, the business logic of these data quality checks actually isn't that complicated. We're doing kind of basic null checking, type checking, arithmetic. There's not a lot of business logic. We just need raw compute. So they had the bright idea of, let's write the data quality test framework in Rust. And so the person bringing in Dagster goes to the data quality person and they say, hey, I really want to incorporate this in Dagster, but you can't do it. I need you to port it to Python. And that person says, as our theme, instead of me having to port and migrate stuff, how about I don't do that? How about I use the tool that was great for this? And pipes allows a solution. You can write business logic in potentially any programming language, and you can participate in Dagster in a first-class way. Let's see how that works. So the first thing we're going to do is actually write the Rust protocol itself. So this is the code we need actually to write pipes compliant code in the Rust process which executes Kubernetes. You'll see here we have this context object which contains a partition key. And what this is actually doing is we need to construct the context object. And all we've done is we say that in order to be a pipes compliant client here, you stuff in a JSON serialized representation of that context, you zip it in your base64 encode it and get it out. Okay, now that's in the process. And then the second part is we need to report back the results of an asset check. And so we have a specified format, a JSON format for this, and it's in JSON schema, but right now we're hand coding it for the purposes of this demo. And then we attach a version number to every single message. And then actually, it might be hard to believe, but actually we found the most reliable way to get data out of the Kubernetes pod is actually just to put in a JSON line into standard out. And so we're just literally printing it out, and then our reader on the other side reads that, and every time it encounters a line, it's a JSON line that it can parse with that version number, it says, hey, this is a structured message. That's actually how the Python implementation works, and the Rust implementation works exactly the same way. So now that we've written the protocol, now we just need to write the business logic, which uses that protocol to communicate the information. So this is what the pipes programmer in Rust would write. You will call this function open pipes context. You have the pipes context object. You pass the partition key into the business logic. We abstracted it out. Imagine that's polars, and it loads the data frame into memory and does a bunch of computation. It checks to see if the data quality check passed. And then it calls this report asset check function, which literally all it ends up doing is spitting out a JSON serialized object standard out. But we've reported whether or not the data quality check passed and some meta information about it, meaning so that the user knows how many null values there are. So now let's hop into a live demo of adding that Rust-based asset check to a real project. We're going to continue building on the example we did before. So here we have the external assets from the data lake, where the orchestration is happening elsewhere. We have this asset, which is taking the results from that lake and doing some processing, and is doing it using pipes. Here's the sensor, which kicks off the run every time the lake gets updated. And now we have the asset check. If we go to this definition, this is what an asset check looks like. It says what asset it applies to. The name of the check is the function name. And then in this case, all we do is we invoke the pipes Kate's client, and that looks very similar to the code we had before, right? It looks like effectively identical. We just have to get an asset check result instead of a materialized result. Now, if we go to the code that it gets invoked on the other side, it looks like this. And this is Rust code. It actually looks very similar to the pipes code we had in Python. We try to for these language SDKs, we anticipate making it feel familiar and have familiar styles within the idioms of the language so that you can have uniformity across the experiences. So we open up the pipes context, and then we do, I am abstracting away the actual business logic, but imagine this does a bunch of null checks. And then we report back the results of that asset check back. And in effect, the plumbing of pipes, to use the cheesy analogy, ends up serializing a message and getting it in this format, which our framework can understand. Now, when we load this up in our UI, this is what it looks like. So I'll zoom in here. And if we go in, let me reload this. Okay, I reloaded that. I had just added the check. And so now there's a check here, right? And we haven't evaluated it yet. This is how the asset check works. We go back here. Let me find here. And so I'm going to kick off the external lake. So you'll see these come in. And I'll show you this is just a standard Docker file that backs the check here. We've built this previously. Now these have all materialized. Let's go over here to our sensor. Oh, it's not on yet, so I'm going to turn it on. And now it's kicked off a run. We go here, go to the run, and now you'll see there's two steps happening. So it kicks off the actual asset materialization. Now it's going to kick off the next piece of compute, and this is actually going to invoke Rust. And let's just wait for a second here. We're doing this, and look at that. Asset check passed, null count. We have just incorporated an asset check built in Rust into our pipeline. And you can see here, it kicked off a new run. Because I'm continuing to flow things into the lake. So we can go here, but we can on the right-hand side here. Now the check has passed. We have the count. We can go in the asset catalog, see that it's materialized a partition, and that we have our checks all right here. And so that's how we fully integrate the system. So we just completed our last demo. It was a bit of a doozy, but I think we've really shown here with combining pipes and external assets, we've really made Dagster a much more flexible and powerful system. We demonstrated how using external assets, you could take a completely pre-existing orchestration infrastructure and lightly instrument it, and then be able to monitor and track that and visualize lineage in Dagster for that existing infrastructure without a heavyweight migration. Then we were able to show how an ML team could adopt it and then use pipes, which is this, again, this protocol for invoking remote compute, while still having that remote compute feel like it's a first-class participant in the data platform. And the machine learning team was able to do that to invoke arbitrary tasks and arbitrary case containers and seamlessly pass parameters and get back structured metadata. And then by linking those things together, the ML team could do event-based scheduling based on what's going on upstream in the data engineering team, which is super exciting. And then we demonstrated this feature about how pipes, given that it's a protocol that works on serializable data, we're going to be able to do pipes implementations in more than Python. There's a world beyond Python. So we demonstrated, the people writing data quality texts in Rust and having it appear in Dagster in a first-class way. So what are we launching today? That was a big future here. On a very practical basis, this is what we're launching today. We are launching an implementation of pipes in Python. In terms of invoking pipes computations, we're launching 4 clients. One is an arbitrary subprocess, it's like a script on your machine, a Docker container, Kubernetes pods, right, which is a critical use case, very common, and then also Databricks jobs. And I think what's maybe even more exciting is that this is all those clients are fairly thin clients in the best possible way with minimum amounts of specialization that's built on a generalizable framework that's pluggable and usable already for people to customize the protocol for their own context. There's no way we can anticipate everywhere that people are going to want to use this. So this is designed to be pluggable and composable, so it can be used anywhere in any cloud in any runtime. And we're just getting started. I think this is the future of, there's enormous possibilities here. And a lot of our future roadmap is going to be determined by feedback and early usage. So I highly encourage you to check it out, look at our docs, maybe try to spin up a client yourself, and then think about in your platform, what would be the most useful? Where should we focus on next? What programming languages? What technologies? What features of pipes do we need? There's going to be a ton of work in this area going forward. But I couldn't be more excited about the future. So that's it. I'm glad. Thank you for coming to launch week. We've launched a bunch of exciting new features, and I hope you have a good weekend. Thank you very much.